Alright, so now we're going to work through this practice packet. And before we really jump into it, I want to say a couple of things. I think all of these problems are fantastic, or at least where these problems came from historically has been very good, and I think every problem kind of helps build your conceptual and mathematical abilities with them. So I encourage you to work through this. And I want to give you full disclosure. I'm intentionally not looking through the questions. I kind of glanced at them as I was cropping them out to different pages, because I want you to see my thought process as I'm working through the problems. So there may be a time where we get to a problem that will get into a sticky situation, and if it's really bad, I'll have to pause the video and edit it, but I don't foresee that happening. We'll see. The other thing is, I encourage you, before we start any problem, to pause it, look at the problem, try to work through it on your own, and see if you do the same as I do. And I will try to upload timestamps in a comment down below the video. So if you're looking for them and you're only looking for one or two problems because you worked through this set of problems entirely on your own, please feel free to do so and find the problem that you're looking for, so that way you don't have to watch what may end up being an 1.5 hour long video for one single problem. Excuse me. So without further ado, we're going to get started. And as a reminder, this is simple harmonic oscillators, springs and masses and pendulums. So the first one I see: when a body executes simple harmonic motion, its period is, and then I'm looking at the answers, the reciprocal of its period, or the reciprocal of its speed. That's not true because it's the reciprocal of its frequency. It's not proportional to amplitude because our two equations, period of a spring is 2 pi times the square root of mass over the spring constant, and period of a pendulum is 2 pi square root times length over gravity. Neither of those have to do with amplitude, so it has nothing to do with that. The period has nothing to do with acceleration. It is independent of its amplitude, so right there I'm thinking that's the case, but I'm still going to double check because it doesn't take any time. It doesn't take much time to check one last answer. And it, again, has nothing to do with acceleration. So the answer to number 1 is 4, independent of its amplitude. Problem number 2. The displacement in simple harmonic motion is at a maximum when before I even get started, I'm going to think of what a harmonic oscillator is. I'm going to call this position B, and it's going to swing over to position A. And this A represents amplitude. And then it's also going to go over to position C. So the displacement is at a maximum. So the displacement's at a maximum at positions A and C. And right off the bat, I know kinetic energy is not at a maximum because that's when it comes to a stop. Kinetic energy is at a maximum at position B. Kinetic and velocity are at a maximum. Because think about it, when you're on a swing, and you could have also done this with a pendulum if you wanted, and the positions would still be the same because pendulums and mass oscillators are very, very similar. The kinetic energy and velocity are at a maximum when you're at the bottom of the swing. So kinetic energy is not at a maximum when displacement is at a maximum. The velocity is 0. That's looking correct to me. Velocity is not at a maximum. Momentum is mass times velocity, and if velocity is at a minimum, then momentum's also at a minimum. And the acceleration is not 0 because acceleration is caused by unbalanced forces. So if we're looking at a mass on a spring, acceleration is 0 at the middle point because the spring is not stretched or compressed. So there's no force, so there's no acceleration. So acceleration is 0 at position B and maximum at positions A and C. And remember that equation for how strong the force is equal to kx. So a bigger displacement means a bigger force. So the answer is 2. Velocity is 0. Okay, whenever I look at a problem, and this is where you get to see some insight into my thought process, I glance at the graph, I glance at the answer choices, and then I read the question. So right off the bat, I see a position time graph. I know it's starting at max position, and that's really all I'm going to look at. I'm not going to look at it incredibly closely. I'm just going to get a rough idea of what the graph is. So we have a position time graph, and then I'm going to glance at the answer choices. At point P, the mass has, and then all of these options. And you can probably skip the question. I don't ever recommend doing that because oftentimes they'll give you a red herring. So they have to do with the velocity and the acceleration. Is it positive? Is it negative? Or is it 0? So mass is attached to a spring and oscillates back and forth in a position time graph. So at point P, we know that it's and if you're unsure, you can translate it to a graph, which I don't think I need to do, but it never hurts. We have position A, B, and C, where A and C are at max stretch and max compression, and B is the equilibrium point. So at max position, that would be position C, equilibrium position is B, this would be A, negative amplitude, back to B, and then up here would be C. So you can see it's oscillating C, B, A, B, C. So it's between position B and C, and it is traveling closer to position C. So in this picture, and in this problem, at position P, the object is here and it's traveling towards position C. So it does have a positive velocity. Now, how do we find acceleration? Again, acceleration is directly proportional to the force. So at position P, which direction is the force? Well, the spring is trying to pull it backwards, so the force is to the left. And if force is to the left, acceleration is to the left. And in physics, we treat to the left as negative. So it has positive velocity and negative acceleration. Negative acceleration, negative acceleration. Oh, there's negative acceleration and positive velocity. So the answer should be 6. Positive velocity and negative acceleration. Number 4. Again, I'm looking at the graph first. We have Z versus T. Oh boy, and we have A, B, C, and D. And then the answer choices are A, B, C, or D can be true. So this one might come down to process of elimination. You always have that tool in your back pocket. So now I'm going to look at the question. A mass suspended from a spring is oscillating vertically up and down. So we have a mass on a spring oscillating back and forth between positions A, B, and C, where C is your equilibrium point, or I'm sorry, B is your equilibrium point. C is max amplitude, and A is max amplitude in the opposite direction. At some point during the oscillation, the mass has 0 velocity, but acceleration is non-zero, can be positive or negative. Well, we found from the last problem that when it's at either position C or position A, the velocity is 0, and the acceleration is at a maximum, because acceleration is directly proportional to the force. So when it's at max stretch, position C, the force is the greatest, the acceleration is greatest, and the velocity is in fact 0. So A is definitely true. At some point during the oscillation, the mass has 0 velocity and 0 acceleration. Well, the only two places where it has 0 velocity are positions A and C. And at position A, with a vertical accelerator, it's not necessarily being pulled down by the spring, but that's where it's coming to a relaxed position. So the spring is not really stretched, nor is it compressed, but it's accelerating because the object at that point is being pulled down by gravity. So in both of those situations, there is an unbalanced force, which means there is an acceleration. So at some point during the oscillation, it has zero velocity and zero acceleration. That's not possible, so we've ruled B out. At some point during the oscillation, the mass has non-zero velocity, but has zero acceleration. That one's tough. I'm going to come back to that one. And D, at all points during the oscillation, it has non-zero velocity and has non-zero acceleration. Well, we know from position, there's plenty of points where it does have velocity. If it moves at all, it can't have non-zero velocity. So we've ruled out B and D. So B is wrong, B is wrong, D is wrong, D is wrong, D is wrong. And B and D are definitely both wrong. So now we have it down to a 1, 2, 3, 4 options. And obviously on the AP test, you're not going to have this many options. I haven't seen any problems coming anywhere close to this. But I think that's also what makes these questions valuable, is they don't quite give it to you, they make you reason it out. Well, we know A has to be true. So any option that doesn't include A is wrong. So 10 is wrong, 5 is wrong. So now we have ourselves down to a 50-50 shot. It's either A or A and C. So now we have to see if C truly is correct. At some point during the oscillation, it has non-zero velocity. So that's anywhere other than A or C, because those 2 points has zero velocity, but has zero acceleration. And that can't be true because it's going to be moving from C up to A. But during that time, if the spring is equal to the force of gravity. So if the spring force equals the force of gravity, then it would be true. Alright, so as it oscillates down, the spring force is up and the force of gravity is down. The force of gravity never changes. Spring force gets weaker and weaker and weaker and weaker. So I would say there has to be a point where that's true, because up here the spring force should be equal to 0. And down here, the spring force is significantly greater than the force of gravity. So as the box travels from position C to position A, the weight of the box doesn't change, but the spring force goes from less than gravity to, the spring force goes from greater than gravity to less than gravity. So at some point during that transition, they have to be equal, at which point it does have non-zero velocity and has zero acceleration. So A and C are both true. So option 6, that was a tricky one. All right, number 5. When an object is oscillating in simple harmonic motion, and I'm going to skip and look at the answers. We have speed and magnitude of restoring force, and they're looking at zeros, maximums, minimums, half maximums. So I'm just going to picture box oscillating from A to B to C, where of course B is my equilibrium position and A and C are the maximums. When it's oscillating and it's at its maximum displacement, so A or C, from the equilibrium position, which of the following is true of the values of its speed and the magnitude of its restoring force? Well, at A and C, the speed is 0. So right there, we've knocked it down to answers 1 or 3. And the restoring force is at a maximum at positions A and C, because the restoring force is caused by the spring. So when it's max stretched at C, as it gets closer to C, it gets stronger. And as it gets closer to A, it's stronger. So it has to be a maximum. So your answer choice is 1. 0 speed, but max restoring force. Number 6, 7, and 8. Simple harmonic oscillator takes 11.6 seconds. They want us to find the period to undergo 5 complete vibrations. And remember, one vibration is saying the same as one oscillation. And the period is the amount of time for one full cycle. So if it does 5 cycles in 11.6 seconds, we're going to take 11.6 seconds for 5 cycles. And that's going to give us 2.32 seconds per oscillation, or 2.32 seconds for one full period. So 2.32 seconds. Number 7, calculate the frequency. And remember, frequency is the inverse of the period. So 1 over 2.32 is going to give us a frequency of 0.431 oscillations per second. Oscillations per second, also known as hertz, or vibrations per second. Now, this is a good time to talk about frequency and period and how they're inverses. Both of them tell you the exact same information. It tells you it takes 2.32 seconds to do one full oscillation, or it does 0.43 oscillations every second. So hertz is oscillations per second, period is seconds per oscillation. So 0.431 hertz. And find the angular frequency or angular velocity in radians per second. And remember the equation, 2 pi over frequency, 2 pi over the angular velocity equals 1 over the frequency. It's also equal to the period. And this equation is also on your equation sheet. I'm going to use this second one, and I'm going to cross multiply and say 2 pi f equals the angular frequency or angular velocity. Both those terms mean the same thing. I want to make that clear now. So then we just take our frequency and multiply it by 2 pi. And you're going to get 2.71 radians per second. Number 9. We have a position time graph, and they want to know the angular frequency. T equals 2 pi over the angular frequency, which is also equal to 1 over the frequency. I'm going to actually use the first 2/3 of the equation and cross multiply t times omega equals 2 pi. And the reason I'm doing that is because period is super easy to find with a graph. It's the number of time from crest to crest. So I know the period right off the jump is 5 seconds. So angular velocity is going to be 2 pi divided by 5 seconds. And I look at my answer choices and realize pi is not in the answer choices. So you need to make sure you multiply 2 times 3.14 and divide that by 5. and we will get 1.256. Did I do a thing wrong? Two times 3.4 divided by 5. And now I'm realizing that I can't even measure because this is from 1 to 5 seconds. So the period is actually 4 seconds. So it should be 2 pi divided by 4. And when you do that, you're going to get 1.57 radians per second, or 1.6 radians per second. Sorry about that. So this is actually a good learning moment. Make sure when you're looking at your graph, you are measuring crest to crest. We could have also measured from the beginning of the wave to the beginning of the next wave, which would have been 4 seconds as well. So no matter where you measure it, you're still going to get the same period. All right, number 10. Particle oscillates up and down in simple harmonic motion. Its height, y, as a function of time is shown in the graph below. And I didn't even follow my rules. I forgot to look at the graph. But the more you do it, the better practice you'll have, and the more likely you'll be to do it on the test. My answer choices are they're looking for times. At what time during the period does the particle achieve its maximum acceleration? Keep in mind, maximum acceleration is caused by force. So as it oscillates from position A to position B to position C, it's going to be at the greatest when the restoring force is the greatest. The maximum positive acceleration, meaning it's being pulled upwards with the most amount of force. So F equals kx. So when the position is greatest, it's going to be pulled upward the greatest. So this would be -5, 0, and +5. So at -5 is where it's the greatest, and we look at the graph, and that happens at time equals 1 second. And since that option doesn't exist, we have to assume that 5 and 5 aren't necessarily positive or negative. It could be either or. I don't understand why they feel that way, but the force is greatest when amplitude is greatest, so your only other option has to be when time equals 3 seconds. Not the best, but I'm going to have to roll with it. 11. A mass is placed on a spring and oscillates with a period of 1 second. So this is different where it's on a stiff spring, so it's chink, 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 oscillating up and down on top of the spring. And now a heavier mass is placed on the same spring. Which statements are true? So we have 6 statements, and we have options to which ones are or are not true. The heavier mass oscillates with shorter period because the gravitational force on it is greater. Well, keep in mind the period of a spring is 2 pi times the square root of mass over the spring constant. Gravity has nothing to do with changing the period of an oscillator. So 1 is not true. 2. The heavier mass oscillates with the same period because gravitational acceleration is constant. Well, more mass is going to increase the numerator, which is going to increase the entire right side of the equation, which means the period also has to be greater. So it's not going to be the same period, so we've ruled out 2. The heavier mass oscillates with a longer period because of its greater inertia. That's why mass affects the period. It's because it takes longer to speed it up and slow it down, so it has a longer period. Think about shaking a small box versus a heavy box. The heavy box is going to take you more effort and more time to shake it back and forth than the light box. So more mass, more period because of inertia. So the heavier mass oscillates with a longer period because of its inertia. So 3 is true. Heavier mass must have greater mechanical energy than the first because it is heavier. Well, if we look at position C, when it's stretched out most, its full mechanical energy is equal to potential energy, which is equal to 1/2 kx squared. There's also gravitational potential energy because it's vertical, but the same principle still applies. So the heavier mass must have greater mechanical energy than the first because it is heavier. And mass doesn't play into that. So that's not true. So we can rule out 4. 5 is the heavier mass must have less mechanical energy because it moves more slowly. Again, mass isn't playing a factor in the potential energy, and one cannot reach any mechanical energy without knowing the amplitude of motion in each case. Oh, that could change things. But I'm going to assume it doesn't. I don't believe that it does. Because I assume based on the question that they're placing it on when it's already at the maximum amplitude, so it shouldn't change it. No, I'm definitely wrong on that. So actually, I do think that's true. I think... Alright, after taking some time to think about it, I'm sorry, I was wrong. The heavier mass does have greater mechanical energy than the first because mechanical energy is the total energy, so it's the potential energy of the spring plus the potential energy due to gravity. So mgh. So more mass would mean more gravitational potential energy, which does mean more mechanical energy. I'm sorry for that mistake, but the answer is 3 and 4. All right, we have a 3-part problem. A weight suspended from a spring is seen to bob up and down over a distance of 11 centimeters twice each second. So we're going from position A, position B, position C, and bob up and down over 11 centimeters 2 times each second. So 2 oscillations per second. That's 2 hertz. That's our frequency. So, the first question is, what is the frequency? So 2 oscillations per second. The frequency is 2 hertz. What is the period? Well, we know period is the inverse of the frequency, so 1/2 is going to give us 0.5 seconds. And what is the amplitude in centimeters? Well, if 11 centimeters is the max distance it stretches, then half of that would be the amplitude, because amplitude is distance from the equilibrium position to either maximum. So that would be 5.5 centimeters. 15. When a 26-gram mass is attached to a certain spring, it makes 22 vibrations in 4.9 seconds. What is the spring constant? Ooh, there's a lot going on here. So if I see this, I know I need to find spring constant. So K equals question mark. You should always start with your unknown. Mass is equal to 26 grams, and I'm going to immediately convert that to kilograms. And remember, kilo means thousand, so to go from gram to kilogram, you divide by 1,000. We know 22 vibrations in 4.9 seconds, 22 oscillations in 4.9 seconds, and that's going to be measured in oscillations per second, or hertz. So that's going to be our frequency. So 22 divided by 4.9 equals a frequency of 4.49 hertz. So now I'm trying to find spring constant. I need an equation with spring constant. We have Fk equals Kx, that exists, but we don't have the position, we don't have the force, which means that equation is out. So my next thought is, well, what about the period of a spring? 2 pi root m over k. We know mass, we're trying to find spring constant, we know pi, we know 2, and we can find the period because it's the inverse of the frequency. So we're going with that equation. So working through that, period of a spring is 2 pi square root of mass over the spring constant. Well, we're going to need the period. So I'm going to take my frequency and find the inverse of it. And that means that the period is 0.223 seconds. So 0.223 equals 2 pi times the square root of mass, which is 0.026 kilograms, divided by the spring constant. So the first thing I'm going to do is divide both sides by 2 pi. So I can cancel that out. So divided by 2 pi is going to give 0.0354 equals the square root of Vuja over k. And then I'm going to square both sides. And I'm going to shift this up a little bit so I have a little more room. So now I'm going to square both sides. And oh boy, that's becoming very, very small. Now we have 1.26 equals the square root of, oh, excuse me, I forgot my scientific notation. Times 10 to the negative 3 equals 0.026 over k. And at this point, if it's easier for you, you can cross multiply and then solve for k. But I like to just flip both sides of the equation. So I'm going to have 1 over 1.26 times 10 to the negative third, or 796 equals, and don't forget to flip the other side of your equation too, k over 0.026. And then I'm going to multiply both sides of the equation times 0.026 to find a k value of 20.7 newtons per meter. So that's how stiff your spring is. It takes 20.7 newtons to stretch it 1 meter. All right, 16, 17, and 18. I see a diagram. I'm looking at that first. We have a mass on a spring with K. So we know K, we know M. It goes 4 centimeters and then X. So that's confusing. I'm not sure what they're looking for there. They're going to want us to find the period, max speed, and max acceleration. And remember, max acceleration is when amplitude is at a maximum. So let's see what else we have. We know mass equals 0.353 kilograms. Force constant, so K equals 8 newtons per meter. Free to oscillate on a horizontal frictionless track. The mass is displaced 4 centimeters from the equilibrium point and is released from rest. So if they pull it back 4 centimeters and then they release it, which means, oh, excuse me, they pulled it to the left, released it from here. This is where X equals 0, so it's oscillating back and forth. This is position C, B, and A. Minimum, maximum, equilibrium point. So we need to find the period. And this is a spring oscillating, so 2 pi root m over k. And this one will be way more straightforward than the other one. So at this point, it's plug and chug. We know pi, we know mass, and we know the spring constant. So I'm going to plug that into my calculator quickly. And get 1.32 seconds. 2 pi root m over k. And what is the max speed of the mass? So if we're trying to find the max speed, we need to go back to conservation of energy. So the energy at all positions is going to be equal. So your energy at position C equals the energy of position B equals energy at position A. And where is it at a max speed? Position B. So mechanical energy at B equals the mechanical energy at either A or C. I'm just going to fill in C. At position B, it has kinetic energy. And at position C, it's going to have spring potential energy. So 1/2 mvb squared equals 1/2 kxc squared. We can cancel out our halves. That makes life a little bit easier. And we're trying to solve for velocity. So at this point, it becomes plug and chug. And when you do that, you should get an answer of 0.19 meters per second. So now we need to find the maximum acceleration of the mass. To do that, acceleration is greatest when force is greatest. By the way, if you were off by a couple decimals on the previous problem, please make sure you convert centimeters to meters. So instead of 4 centimeters, the amplitude, or x, should have been 0.04 meters. So now we need to do C, or excuse me, number 18, which is maximum acceleration. And acceleration is force divided by mass, but they didn't ask for any acceleration. They want the maximum acceleration. So when it's either at position C or A, because that's when force is greatest. And we know that the force is the spring force, which is equal to kx. We know k is 8, we know x is 0.04, and we know the mass. So when you plug those in, you should get 0.91 meters per second squared. So now I'm going to reattempt this problem for the third time. Now I had to take a moment and walk away from it and come back to it. And then I realized it's a system. And I need to approach this problem as a system. So my first main thought is for the top block, for it to not slip, the time where it's most likely to slip is at position C, where it's at a maximum. So we have a 5 kilogram block on a 7 kilogram block, and it's at position C, meaning maximum amplitude, because that's when acceleration is going to be the greatest. So for the top block, the only force acting on it is the force of friction. So the net force on the top block equals mass times acceleration, or the force of friction equals mass times acceleration. We're trying to figure out what the max amplitude is, and that max amplitude will be the one that will create this acceleration. So the force of friction is mu times the normal force. Mu Fn equals mass times acceleration, or mu mg equals mass times acceleration. Mass cancels out on both sides, so mu g equals acceleration. But that doesn't tell us anything about the max amplitude. We have to find the max amplitude, and for that, that's where I'm going to look at it as a system. So this is for the top block over here, and for the system on the right side. So now we have a 17 kilogram block, where the only force acting on that is the force of the spring. So if we look at the net force equation for that, we can use this acceleration, or we can use mu times gravity to find the acceleration and then plug it into here because the force of the spring is equal to kx at max amplitude. We know k, we know mass, and acceleration is equal to mu times gravity. So the max amplitude is mu mg over k. We know mu, we know m, we know g, but we don't know k. And that's where the final equation comes in, and that's the period of a spring. So the period of a spring is 2 pi times the square root of mass over k. We don't know the period, but we know period is the inverse of frequency. So 1 over the frequency equals 2 pi times the square root of m over k. And then you plug in frequency, you plug in 3.14, and you plug in the mass. In this case, it's the full 17 kilograms because that's the full mass being oscillated on this period. And you can use that to isolate a k value of 3,515 newtons per meter. And once you have that value, then you can plug it into here. We have k, we have g, we have mass, which is, again, the full 17 kilograms because this is for the system. And we know the coefficient of static friction. So you can use that to find the maximum displacement of 0.015 meters. But keep in mind, this question specifically asks for units in centimeters. So in that case, it would be 1.53 centimeters. Number 20. Ooh, we have a bunch of graphs. Right here, I see a position, I see displacement, and these are looking at kinetic versus displacement. So I'm sure with this potential energy versus position graph, they want us to figure out kinetic. So the graph below represents potential energy U as a function of displacement, as we predicted, for a mass oscillating on the end of a spring. And you guys know what this looks like: position A, B, and C, with amplitude x max. The graph represents the kinetic energy. Which graph represents the kinetic energy as a function of displacement x? Well, right in the middle, we see that potential energy is 0 at position equals 0. So this is position B in our graph above, so that's when kinetic has to be a max. So kinetic energy to max, kinetic energy to max, kinetic energy to max, max. So we've ruled out 5, 3, and 1. And at negative x and positive x, it has to be at a minimum because that's when the velocity is 0 at positions A and C. So no, we've ruled out 2. No, we've ruled out 4. And that eliminates it down to option 6 or 7. Now, if the position versus time graph is a U shape, and position and kinetic energy are inverses of each other, that means it also has to be a U shape. So that leaves only one option, and that's option number 7. All right, 21 through 23. 21 is asking us to calculate the total energy of the system in joules. All right. So the mass of 378 grams is connected to a light spring of force constant K, 31.9, oscillates on a horizontal frictionless track. We know what that looks like. A, B, C. And the amplitude of motion is 8.6 centimeters, or 0.86 meters. And that's our amplitude. And they want us to figure out the total energy of the system. Well, the total energy is equal to the kinetic plus the potential at any given point. I'm just going to go ahead and calculate it at position C. At position C, the mechanical energy is all potential. there is no kinetic because that's where it comes to a stop, so the velocity is 0, so the kinetic is 0. So the mechanical at C is 1/2 kx squared, and then you plug in your k value and your x value into a calculator to find that the total potential energy is 0.118 joules. And I'm sure you guys already caught it, but I want to point out that I converted my unit wrong. 8.6 centimeters is not 0.86 meters, it's rather 0.086 meters. Because remember, 100 cents in a dollar, 100 centimeters in a meter. So I apologize for that, but if you plug in that K and that X value, you should get 0.118 joules. Number 22, what is the max speed? Anytime you see a problem like this, it's conservation of energy. Max speed, your first thought should always be conservation of energy. And it won't always be the case, but most of the time it will. So where is our max energy going to occur? Well, that's going to happen at the equilibrium point, at position B. So I'm going to use conservation of energy since we already have the total energy. That's equal to the energy at position B. And I'm going to actually, move what we have up here. In fact, I'm just going to shift everything nowhere because I need to see all of that. I'm going to select, that's my issue. Give me 1 second. And now that I've cleared my board, we know that the mechanical energy is 0.118 joules. That's the total energy at any position. So I'm going to set that equal to the mechanical energy, use that as the energy at position B, which is equal to the kinetic at B plus the potential at B. But since the spring is not stretched or compressed at B, 100% of the energy is kinetic, or 1/2 mv squared. And that's equal to 0.118 joules. And then you plug in the mass and you solve for a velocity of 0.79 meters per second. When you're doing that calculation, please make sure that you're taking the square root at the end of everything, and make sure that you're converting your mass of 0.378 grams to kilograms, or divide by 1,000. Looking at 23, what is the magnitude of the velocity when the displacement is 5.1 centimeters? So now we have a weird situation where we're actually at position D. So we have A, which is the minimum amplitude, B, equilibrium point, C, where it's stretched, and then now we have this magical position D where it's not stretched the whole way, but it's only stretched 0.051 meters. But we're still going to use the mechanical energy. So if I clear this area, give myself some room, I'm going to use the mechanical energy at D. So the mechanical energy at D equals the kinetic at D plus the potential at D, because the total energy never changes. So 0.118 joules equals 1/2 mv squared at D plus 1/2 kx squared at D. And then you plug in your values. You use your x equals 0.051 meters. We know the mass is 0.378. We know the k value is 31.9 newtons per meter. And with some algebra, and I will walk through this one because the algebra does get a little bit more involved. Let's calculate the kinetic energy. 0.5 times 0.378 times the velocity. Oh, we're trying to find that. So we get 0.189 v squared plus 0.5 times 31.9 times 0.051 squared is 0.0415 0.5 joules. So now we're going to subtract that from both sides, 0.118 minus that answer we just got, to get 0.077-ish joules equals 0.189 times v squared. And since we're trying to isolate for v squared, we're going to divide by 0.189 and then take the square root. And you should get a velocity equal to 0.636 meters per second. And they do want it in meters per second, so we're set on that problem. Moving right along. 24. And looks like we're getting to pendulums. Jim and Gina are swinging on adjacent equal lengths at the school playground. Jim weighs about twice as much as Gina. So who, if either of them, takes less time to swing back and forth? Well, to figure out the time to swing back and forth, that's a period. And the period of a pendulum is 2 pi times the square root of length over gravity. The length is the same, gravity is the same, and pi never changes. They should take the same amount of time. What, if anything, will change if Jim swings while standing on the seat of a swing? Now here is a really tricky question, or at least one that needs to be approached at least once. If Gina is sitting, then the length of the pendulum is the length to her center of mass, which is right around there. However, if Jim is standing on the swing, now his center of mass, or the length to his center of mass, is ever so slightly higher than Gina's. So her length is longer. And if you have a bigger length, you're going to have a bigger period. So Gina's period will not decrease. Jim's period will decrease. He has a smaller length. I was approaching the question from the wrong direction, but he has a smaller length, which means he has a smaller numerator. The right side of the equation decreases, which means his period also decreases. So his period actually gets smaller when he stands on the swing, which makes sense. He makes an essentially shorter swing to his center of mass. All right, a pendulum has a length of 4.6 meters. Find its period. And that question should tell you all you need to know about periods of pendulums. Length is the only thing that matters. So the period of a pendulum is 2 pi times the square root of length over gravity. We know 2 pi is 6.28. Yes, that is rounded. I don't care. It usually doesn't matter. 4.6 over 10. So 0.46. Take the square root of that and multiply it by 2 pi. And you're going to get 4.3-ish seconds. How long would the pendulum have to be to double the period? So we're going to try to find the length. And we need double the period. So instead of 4.3, we're going to use 8. It actually comes out to be 8.52 seconds to truly double the period without rounding. Or at least without rounding as badly as I did before. So 8.52 equals 2 pi times the square root of our new length divided by gravity, which is still 10. So 8.52 divided by 2 pi squared, and then we're going to multiply that by 10, and you should get 18.4 meters for the new length. Having landed on a newly discovered planet, an astronaut sets up a pendulum of length 1.62 and finds that it makes 301 oscillations in 563 seconds. So right there, I'm thinking, okay, they're telling us the frequency. 301 oscillations in 563 seconds. So the frequency is oscillations per second. So 301 divided by 563 is 0.535 hertz, which also tells us the period because period is the inverse of the frequency. So if we do that, we're going to find the period of one oscillation is 1.87 seconds. So a little bit less than every 2 seconds it's going to swing all the way back and forth one time. The amplitude is very small compared to the pendulum's length. That's just telling you it's not making a very big angle. And something we haven't discussed before, but is important in higher level physics, is the small angle approximation. We use this equation t equals 2 pi root L over g, which doesn't have anything to do with the angle. And the angle doesn't really make a difference in the period as long as the angle is small enough. When you get to steeper and steeper angles, then it does have an effect. And this is called the small angle approximation, and we will, from now on, be ignoring it. So now that we're back to ignoring it, we have the period, we have the length, and now we need to find g. Well, you have one equation for pendulums. Tp equals 2 pi times the square root of length over gravity. We know the period is 1.87 equals 2 pi, or 6.28. 2 times 3.14 times the square root of length over gravity, which in AP1 is always rounded to 10. So 1.87 divided by 2 pi. And then we're going to square that, square both sides of the equation, and then multiply by 10 to isolate for length. And you should get the length of the string is 0.887 meters long. Wait. Oh, no. We were trying to find gravity. I did that calculation wrong. I apologize. Allow me to fix it. Where did I get the length from? Oh, I made the assumption that gravity is 10. Gravity is not 10. We're on a new planet. So if you caught that while I was working through it, kudos to you. All right, but still the same idea. 1.87 equals 2 pi, or 6.28, times the square root of our length, 1.62 meters, over the gravity of this unknown planet. That's also a good hint for you when you're looking at these problems. Unless they say you're on Earth, it's not fair to assume gravity is 10. So don't make that leap like habit has taught me to. So we're going to take 1.87 divided by 2 pi, square both sides, and now we get 0.09-ish equals 1.62 over gravity, and you can cross multiply if you need to, or you can just swap these two. So 1.62 over 0.09-ish will give you gravity. So gravity equals 18.3 meters per second squared. All right, we have a simple pendulum consisted of a brass sphere of mass 1 kilogram. Again, mass doesn't matter for pendulums. On a string of length roughly 1 meter. That does matter. The pendulum oscillates with an amplitude of 1 centimeter. Amplitude doesn't matter for pendulums. And period of 2 seconds. Which of the following alterations will change the period of the pendulum to 1 second? What was the old period? Oh, it was 2 seconds. So we need to cut the period in half. The period of a pendulum is 2 pi times the square root of length over gravity. So if we want the period to get smaller, that means we would need length to get smaller or gravity to get bigger. Amplitude has no effect. Using a shorter length, that could have an effect, but we don't know if the length is right. Using a longer string, that's not true. Heavier brass sphere, mass has no effect. Using a lighter mass sphere, mass has no effect. Using a longer string, bigger string would mean bigger period, so that's not true. Increasing the amplitude, so that's not true either. So the answer has to be using shorter strength of length L prime of 0.25 meters. And if you weren't sure, you could have plugged in this new length and seen what the new period was. But of course, before you do that, this is that situation where I was saying you can't assume gravity is on Earth. So you would have to plug in the original length to figure out what gravity was on whatever planet this was, and then you would find gravity equals Vujja. And then you could take that Vujja gravity and plug it in for this new length and see if the new period truly was 2 seconds. Number 30. Pendulum with a period of 1 second on Earth where gravity is g is taken to another planet where its period is 2 seconds. So its period gets doubled. The acceleration due to gravity is most nearly... Well, you could start it... You can do this two ways. You can do it algebraically, or you could do it with proportionalities. The period of a pendulum is 2 pi times the square root of length over gravity. And I'll show you both ways. The first is using algebra. We're going to work our way backwards and figure out, okay, if gravity is 10 on Earth and the period of the pendulum is 1 second, what's the length of the string? Let's find that first. 6.28 times the square root of whatever this length is over 10. So 1 divided by 6.28, square both sides, and then multiply by 10. So you would find the string is length equal to 0.25 meters. So we're going to take that 0.25 meter string to the other planet. And now we know the period is 2 seconds. So 2 seconds equals 6.28 times the square root of 0.25 over new gravity, which I'm going to call Gn for new gravity, and solve for new gravity. So 2 divided by 6.28, square both sides, and then 0.25 divided by that answer. And you will get 2.5, or rather 2.46 equals new gravity, which is how many times Earth's gravity? It's about, well, 2.46 divided by 10 is about 1/4 of gravity. So gravity, or acceleration of gravity, is our gravity divided by 4. Now, if you prefer proportionalities, you absolutely can do that. Period of a pendulum is 2 pi times the square root of length over gravity. And really, we're seeing how the period of a pendulum is affected by gravity. So Tp is proportional to, we basically ignore everything else, the square root of 1 over gravity. But we're trying to solve it for seeing what happens to gravity. So I'm going to square both sides. Tp squared is proportional to 1 over gravity. And the reason I'm doing this is I'm trying to solve for g by itself. So I want g in the numerator, so I'm going to flip it up. So then I'm going to find gravity, but if you flip one side, you have to flip the other, is 1 over Tp squared. And what are we doing to the period of the pendulum? We're doubling it. So 1 over 2 times, but that 2 times is getting squared, will tell us, and by the way, these should be proportionality symbols, will tell us what happens to gravity. So gravity is actually 1/4, which is exactly what we found. So you can do it either way. Find which way works for you. there's always different ways to skin a cat. All right, 4 problems left if I'm not mistaken, maybe 5. A 0.37 kilogram pendulum bob passes through the lowest part of its path at a speed of v. The acceleration is v. What is the tension in the pendulum if the pendulum is 90 centimeters long? So right off the bat, I'm thinking diagram. So we have tension up, and we have the force of gravity downward. Fg equals mg, and tension up. And anytime you're asked about the velocity in a pendulum problem, it's either conservation of energy or it's centripetal motion. If they're asking us to calculate the tension, then your first thought should be, oh, that's centripetal motion. Centripetal force is mv squared over r. We know the radius, we know the mass, we don't know the velocity. We do know the velocity. Oh, hot dog, that makes life easy. And remember, centripetal force is forces towards the center minus forces away from the center. So tension minus the force of gravity equals mv squared over r. And if you solve this equation for the tension, you're going to find that it is equal to 7.35 newtons. One thing I want you to realize is the radius is 0.9 meters. You got to make sure you convert your centimeters to meters. We know the velocity was 2.98. We know the mass, and Fg is mass times gravity, so 0.37 times 10. So when the pendulum reaches its highest point, what angle does it make with the vertical? So we need to figure out this angle up in here. And I'm going to basically tell you my thought process before I get into the bulk of this problem. And it is going to be a slightly bulky problem. Down at position B, we know it has kinetic energy, and at position C, we know it has gravitational potential energy. And that potential energy is equal to mgh. We know the mass, and we know the height is going to be the height that it lifts up from position B to get to position C. By the way, this problem is extremely common, and you need to be able to work through this. So if you're not comfortable with it, I would spend a little bit of time getting more comfortable with it. So I'm going to use kinetic energy at B equals potential at C and trying to work my way through it. So 1/2 mv squared equals mgh. But before I do that, I'm going to go ahead and explain to you where this is eventually going. Once we have the height, then you can use that height and subtract it from the total length of the string to figure out the adjacent side of this upper blue triangle. So it all comes down to this blue triangle where the hypotenuse is the full length of the string. You need the adjacent side, and you get the adjacent side from subtracting the height from the full length of the string. And then you can use that to calculate theta. So I'm going to shift this over so I have a little bit more room. But before I do, I'm going to fill in 1/2 times 0.37 times the velocity of 2.98 squared equals 0.37. Ooh, mass divides out on both sides, times gravity of 10, times the height that we're trying to calculate. So I'm going to shift this over. And what was the length of the pendulum? 0.9. 0.9. And I know you can't see the entire problem at this point, but you don't really need to with where we are right now. So mass cancels out, and we're going to solve for the height using this equation and finding that it's equal to 0.444 meters, or 44.4 centimeters. So it swings up pretty high. especially since it's only a 0.9 meter string. So now we have the height, and I'm going to switch to red so it stands out a little bit better. So now we have the height. We know the full length of the string, so we can figure out this adjacent side of our triangle up here. So 0.9 minus that 0.444 is going to give you about 45.5 centimeters or 0.456 meters. So now that we have the adjacent side and the hypotenuse of 0.9 meters, because remember the hypotenuse is always the full length of the string, we can calculate theta using using cosine theta equals adjacent over hypotenuse, which is going to yield a theta equal to about 60 degrees. All right, so 33, what is the tension in the pendulum when the pendulum reaches its highest point? And I would like to bring you back to that same thing I said in the beginning, where if they're asking you to solve for tension, your thought process should be centripetal force, where Fc is equal to mv squared over r. And this gets a little bit more complex, but not that much, only because it's using angles, which means we need to consider the fact that mg has a horizontal component and a vertical component. So the hypotenuse is the full weight of it. And this is an angle of 60 degrees we calculated. 60 degrees. Which means that this is also a 60-degree angle in here. And this is the adjacent side. So if we look at our centripetal force equation, forces towards the center minus forces away is going to leave us with tension minus the weight equals mv squared over r. And then we basically plug in our values to solve for the tension in the string at this point. The velocity is, at this point, 0. And I want to point out that this Fg is not the full Fg, but rather Fgy, which is going to be mg cosine 60, because cosine deals with the adjacent side, and it's adjacent to the 60-degree angle. So Ft minus mg cosine 60 equals mv squared over r. Well, what's the velocity at the top point? It's 0. At position C, the velocity is 0. So now we can bring mg cosine 60 to the right-hand side. The mass is 0.37 times gravity of 10 is going to give us 3.7 times cosine of 60, which is going to be 1.85 newtons. So the tension at position C is equal to the mg cosine theta. And the final two questions, I think. The final two questions were there. Two clocks are taken from the Earth to the Moon. The first uses a pendulum mechanism. And the second uses a mass spring system. What happens with the time displayed by the pendulum clock? Well, we need to look at our equation. T period of a pendulum is 2 pi times the square root of length over gravity. So the length doesn't change, 2 pi doesn't change, but gravity certainly gets weaker when you go to the moon. So you have a smaller denominator, which is going to make this whole side of the equation get bigger, which means the period of one swing is going to get bigger. And if a clock is taking longer to swing back and forth, that means it's going to travel slower. Similarly, part B is asking, or 35 is asking, what happens to the time by the spring-loaded clock? Well, the period of a spring is 2 pi root m over k. I would hope the mass inside there doesn't change. And I would hope the spring doesn't change. And 2 pi doesn't change, so there's no change. So if you're going to the moon, make sure you take a spring-loaded clock instead of a pendulum clock, because it will yield no change. All right, that concludes all of these problems. I know it was long and involved, but I hope you guys got something out of it and stuck with it. And I'll see you next time. Bye.